So today we talked about rate laws for chemical reactions and how to develop them. And a rate law is designed to give the rate as a function of the concentrations of the reactants at a very specific temperature. Rate laws can be experimentally determined and are not related to any stoichiometry or a balanced chemical equation, and I'm going to show you how to work through some of that today. The first thing you need to know is that the rate law is different than the rate expression. So yesterday's homework was based on the rate expression, and today is the rate law. And the rate law basically allows us to determine how fast a rate is going, or how fast a reaction is going to go, based on the concentration of the reactants. So this is the generic format for the rate law, and as a result of this being the generic format for the rate law, there's a couple of things that we have to keep in mind. K is the rate constant. It will either be given to you, you will have to calculate it, but the K value will change with temperature. So it's always, the rate law is always temperature based. If you have an incredibly large K value, it means that the reaction is going very, very fast. If you have a very, very small rate constant value, it means it's a slow reaction. So it doesn't have anything to do with it being exothermic or endothermic. It's all about the K value. Concentration of one reactant, it would be reactant A. Concentration of another reactant would be reactant B. And if we had another reactant, it would be concentration of C. The exponents here, M and N, are the reaction orders, and we get the reaction orders by calculating them based on experimental data. We don't just grab things from stoichiometry, from a periodic table, or the balanced chemical equation. So we're going to take, and in this particular case, the first reaction is, the first thing that we're going to look at is this reactant here, which is O3. And so in this case, we're going to call this data trial 1 and trial 2. And in the case of trial 1 and trial 2, we're going to be looking at a couple of things. So the first thing that we're going to look at is we're going to look at what happens in terms of concentration from trial 1 to trial 2. Well, 0.44 atm to 0.88 atm, we could say that concentration increased. And it increased by 2. So we're going to say that we doubled it. Now I'm going to put the coefficient of n there up on top, because we're going to try to figure out what that is in a second. Now, what we're going to have to do next is we're going to have to pay attention to what's happening to the rate of the reaction going from trial 1 to trial 2. In this case, it looks like the rate has increased, but we need to figure out how much it's increased by. And so what I'm going to do is I'm going to take 0.03696 and divide it by 0.01848, and I get a value of 2. So the rate also doubled or increased by the same value. So what we have to do is we have to write an expression that says that if the concentration doubles, the rate will also be the same correlation. So 2 to the first power gives me the way the rate double. So in this case, we're going to call this a first order reaction. And when we write the rate law, we're going to say R is equal to the constant times the concentration of O3 to the first power. So that's how we express that. What this really is telling us is that how we increase no matter how we increase the concentration, the rate at which the reaction occurs is going to increase at the same rate. It's a direct relationship. Another example would be this, where I have, looking at potassium iodide, and when I look at potassium iodide, I see that the concentration of potassium iodide is increasing, and 0.88, I'm going to round to 0.9, 0.9 divided by 0.1 for trial 1 and trial 2 gives me a factor that it increased by roughly 9. Now I'm going to look at the rates again, so 7.6 times 10 to the minus 5 divided by 8.4 times 10 to the minus 6, again gives me a value right around 9. So the rate increased by about 9. So in order for us to say that the concentration and the rate increased at the same way, the exponent has to be 1. So 9 to the first power has to equal 9, which is what the data is supporting here. So when we write this is also a first order reaction, and we're going to write it as R is equal to K times Ki over times Ki to the first power. Another reaction that we have here is this reaction with hydrogen peroxide. And when I look at the increase in the concentration of H2O2, I note that 0.56 is roughly 0.6. 0.6 divided by 0.2 gives me an increase by about 3. So it's 3 to the nth power. And when I look at the rate here, what's happening is that the increase in the rate is times 0. And okay, so the rate didn't increase at all. So how we're going to represent that is we're going to say 3 to the 0 power will give us a value of 1, which is essentially what we have here. So the rate never increased. So we're going to call this a 0 order reaction. And so we're going to express it by writing the rate law. Rate is equal to K times the concentration of H2O2 to the 0 power. Now, what is this reaction telling us? This reaction is telling us that no matter how much we increase the concentration of the hydrogen peroxide in this case, the rate at which the reaction takes place is never going to change. So that's what's important to understand about it. And so we're going to talk a little bit more detail about 0 order reactions. And in this case, in a reaction that is a 0 order with respect to a particular reactant, the reaction rates are not affected by changes in concentration. And that's literally what we just kind of expressed before by looking at the data. So when the M value is equal to 0, the rate is expressed essentially by the rate law constant. There's a lot of math on this slide, and so we're going to talk about it in terms of the generic reaction A, reactant A going to products. This is initial time is 0. And this is initial concentration. And when time is T, so this is later in the reaction, the concentration is whatever the concentration is at that point in time. So if we said that the reaction occurred for 20 minutes, then we'd be looking at the concentration at 20 minutes. So the rate expression can be written like that for the reactant, and this is the 0 order rate law for the reactant, and because they're both equal to rate, we can set them equal to one another and get this equation here. Well, that's clunky, and so through the magic of calculus, we are going to integrate this particular statement, and we're going to get the integrated rate law for a 0 order reaction here. I don't think that we need to go through the calculus for this or the integration, but that is what the integrated rate law for the 0 order reaction looks like. And that's useful, but I think it's more useful for us to put it into the y is equal to mx plus b form, so I changed it around for you to look like that. And so now when we graph this, a graph of the concentration at time t versus time will yield a straight line with a negative slope, and like this, where this is my initial concentration, and this would be my concentration as time goes on. So the concentration as time goes on, and this is the concentration, essentially for the graph. Note that the slope is negative k, and note that the title of this graph is concentration of reactant versus time, and that's going to be an important distinction later, because at some point you're going to have to be able to look at a graph and identify if it's a zero order, first order, or second order just by looking at the graph. So these labels are really important here. First order reactions tend to have a rate law that has the m, or the exponent, being a value of 1. And one of the things that we learned, if we double the concentration of the reactant, we double the rate. If we triple the concentration of the reactant, we triple the rate. Again, looking at A going to reactant A going to products, this will be the initial time and the initial concentration. And again, time t would be the end of the reaction, or whenever we stop taking data. So here would be the rate expression for this reaction, and here would be the rate law for this particular reaction, and we set them equal to one another, and we get this expression here, which again is kind of clunky. So again, through the magic of calculus, we get the integrated rate law. And if we put it into y is equal to mx plus b format and we graph it, we are able to get a straight line with a negative slope of k, and I'm going to what that looks like now. And so here is the graph where it's the natural log, that shouldn't be there, but it's the natural log of the concentration of reactant A versus time. You still have your initial concentration, and you still have time increasing, and we still have to look at concentration from that perspective. But essentially, as you increase, or as the reaction goes on, you're decreasing the concentration of A. And so that's what the first order reaction looks like. Note that it's a straight line when you have a relationship between the natural log of the concentration of the reactant versus time. And then second order reactions tend to be exponential. So if we increase concentration of A, so if we double the concentration of A, we get exponential concentration for the rate. So tripling it gets us another exponential concentration or rate value. And so again, initial time, I can't spell. N-I-T-I-A. Initial time, concentration, and then when it's over, when the reaction is over, we stop collecting data. It'll be at time t, and concentration at time t. Again, this is the rate expression that we did last night for homework. This is the rate law. We set them equal to one another. We get this very, very clunky formula. So again, the magic of calculus gives us this integrated rate law for the second order reaction. And I rearranged it to put it into y is equal to mx plus b format so we can slope it, or so we can graph it. And one of the things I want to make sure that you understand or you see is that the slope is going to be positive this time. And when it's positive this time, the graph looks like this. This is still your initial concentration. But your slope is positive as time is going on. So what we're getting at here is that the rate is increasing as we get the inverse, as we use up the inverse concentration of the reactant. So what do we do with those things? Well, those integrated rate laws become very useful in terms of calculating a couple of things. So in this case here, I'm going to tell you that this is a second order rate law, or a second order reaction, with the reaction of NO2 plus NO2 to make N2O4. You're getting the rate constant in this one, and you are getting the initial concentration. So this is concentration of NO2 at time 0. And we're looking for the concentration of NO2 at time 20. So because it's a second order reaction, I'm going to use the integrated rate law that looks like this. And now I'm going to substitute in what I know. So in this case, the concentration of NO2 at time 20 equals K, which is 0.044 per molar per second. And the time, we said it was 20 minutes, but I'm going to change it to seconds because my constant is in seconds, so that becomes 1200 seconds. And we know the initial concentration of NO2 was 0.100 molar. So when I plug these things into so when I start solving this, the unit for seconds cancels out here, so I get something like 52.8 per molar plus 10 per molar here. And so when I add those two things together, I get 1 over 2 at time 20. I get 62.8 per molar. And so when I solve this out to get NO2 by itself, or concentration of NO2 at time 20 by itself, I get a value of 0.0159 molar. So over time, the original concentration decreased from 0.1 to 0.01 to 0.0159 molar. Another example would be a first order reaction. So in this problem, I'm telling you that it's first order. So that tells me that I need to use this formula here. The natural log of A at time final equals negative KT plus the natural log of the concentration of A at time 0. Well, in this case, I know that I'm talking about the reactant ABC at a time of 5 minutes, and comparing it to A, B, C at time 0. So a couple things that I know is I know my constant, I know my time 0, so I'm going to solve for a concentration of A, B, C at 5 minutes when I take the negative of 0.0125 per seconds times the time, again 5 minutes equals 300 seconds, plus the natural log of 0.500 molar. So in solving this out, I get negative 3.75 here plus 0.693 molar. So this gives me negative 4.44 molar when I add that together. And so in order for me to get the concentration of A, B, C by itself, I'm going to take the anti-natural log of negative 4.44 molar, and that will give me my concentration at 5 minutes to be 0.0118 molar. So again, with the first order reaction, as the time went on, we decreased the concentration. And we have one more. In this example here, we're talking about the elimination of alcohol from the bloodstream by humans is a zero order reaction. So that tells me that I'm going to want to use this formula here. Because that's my zero order reaction. The legal maximum for driving is 0.08 grams per 100 milliliters, which corresponds to a concentration of 17.3 millimoles. The rate constant for individuals varies, but it's averaged to be 0.015 grams per milliliter per hour, which comes out to be 3.25 millimoles per hour. So if a person is has ingested enough alcohol to be twice the legal limit for driving. How long will it be before that person can legally drive? Well, we're starting at the initial concentration, so the initial concentration is going to be twice the legal limit. So the twice the legal limit is going to be 17.3 times 2, which is 34.6 millimolar, and I could change that to molar, but I don't think I need to for this particular example. So the final concentration for this individual is 17.3 millimolar. We know that the rate is 3.25 millimolar per hour. And the time is what we're looking for. So this is how long it's going to take this individual to go from twice the legal limit to the legal limit. So the initial concentration is the twice the legal limit, which is 34.6 millimolar. So what that gives me when I start solving this out is negative 17.3 millimolar will equal negative 3.25 millimolar per hour times T, and that will give me a value of 5.32 hours. So it's going to take 5.32 hours for the average human to go from twice the legal limit to the legal limit, which is still not a great idea for driving if you have 0.08. So in my opinion, I think that this individual should stay home, take a nap, drink water. And we will do the second part of this lecture tomorrow, and I will probably make a video for that as well. Hope you guys are feeling better.